Everyone, welcome back to the channel. In today's video, we are going to discuss about chat system. We will design a chat system which is like WhatsApp, Slack or Messenger. So first, let's discuss about functional requirements. In today's video, we are going to focus on core functionalities of the system. So first, as per functional requirement, we should clarify is it one-on-one or group chat. We will focus on one-on-one and group chat both in this video. Second functional requirement is once user created a chat or they are discussing with anyone through the chat, we would like to display online or offline status of the users. We would also like to display message history. And the last one, once somebody delivers the message, we would like to see if the message is already read by the user, by the friend or family. So these are the functional requirements. Now let's focus on non-functional requirements. First, low latency. Low latency is very important because when you're sending a message and if it delivers to your friend, family or coworker after 5 or 10 minutes, that's not a great idea. If they have to wait for 1 hour or longer, there might be some issues. So it's better to have low latency. They should get the message immediately. Second thing is scalability. We would like to scale our system and in future we would like to support millions of users. Third, reliability. And fourth, fault tolerance. We also wanted to make sure that all the messages which are being delivered to other users, we don't lose any of the messages. So these are the functional and non-functional requirements which we are going to focus in our today's video. Now, let's discuss about high-level design. In high-level design, we are going to focus on the major component for the system. And we'll first focus on like very high-level components as I just mentioned. So first, let's start with the user. The user, it might be you or me. Like when we start initiating a conversation, we will first send a message. And that message will be sent to a chat API server via load balancer. Load balancer role is basically like send traffic to available server. It actually tries to balance the traffic between servers. And you might also prefer to go through my previous videos related to load balancer where you can learn more in detail about load balancer. It uses multiple algorithms where you can use like you can decide like round robin or list available connections. There are like many algorithms and based on algorithm, it will send traffic to the next available server. In this case, our next servers, like in this case, we need to send a request to chat servers, chat API servers. And we are going to discuss in detail about chat API servers in our deep dive. In high level, we are just going to focus on that, hey, this is the flow and this is how the request comes. So I will go to the next component from here. Now, once we get the request to chat API servers, it will send a request to queue. Why should we use queue? Well, you can directly send to the user, right? Or you can just save data into the database. But here we will prefer to use queue because we can decouple our component. And there is another benefit of using queue, which is basically like queue has a retry mechanism. Where, let's say you're trying to send a message to a friend and for some reason, maybe there is a network failure or some issues happen. So in that case, if we have configured retry mechanism, then once the message sending fails, it will automatically retry and it will keep trying to send it again to the user until there is a successful. So again, like we can also configure retry, like how many times do we want to retry? It's better to keep the retry less than 5 times because if we try to keep retry 20 times, that's not a great idea. That might also slow down the performance as well as like it will be keep retrying unnecessary. And once it is in retry fails after let's say 5 times, and if retry fails after 5 times, then we can send tag failure to dead letter queue. Basically, like once the data is in dead letter queue, we can go into a manual and look into it like what is the issue and we can resolve the issue. So that way, like we can also find out like this is exactly the issue happening for a particular user. And this is a very high level component. Now, another thing is once we save the data into the database and if another user is not available, we also need to notify the user. And even if it is available, we also need to notify still that, hey, that is message from your friend, from your family, or a coworker. Let's say if it is in Slack, then it might be a coworker. So this is how our high-level design is. Now, let's look into deep dive. In deep dive, we would like to focus on first chat API servers. For chat system, the most important part is communication protocols. How does communication work between user to user, even if it is one-on-one chat or group chat? So, to develop a high-quality design, we should have a basic knowledge of how clients and servers communicate. In a chat system, clients can be either mobile application or web applications. Clients do not communicate directly with each other. Instead, each client connects to a chat service, which supports all the features mentioned earlier. So let's focus on fundamental operations. The chat service must support the following functions: receive messages from other clients. It should also find the right recipients for each message and relay the message to the recipients. And if a recipient is not online, hold the messages for the recipient on the server until she is online. So, when a client intends to start a chat, it connects to the chat service using one or more network protocols. For the chat service, the choice of network protocol is very important. There are a couple of network protocols which are like polling, long polling, and WebSocket. Now let's discuss about protocols. First, we will discuss about polling. As you can see in this figure, polling is a technique that the client periodically asks the server if there are messages available. And if not, then connection will be closed. So it will be keep asking frequently if there are any messages available. Depending on polling frequency, polling could be costly, because here you can see like even though there are no messages, it will be keep checking frequently. Now let's look into long polling, how it works. So long polling, as you can see here, in long polling, a client holds the connection open until there are actually new messages available or timeout threshold has been reached. Once the client receives new messages, it immediately sends another request to the server, restarting the process. But it has few drawbacks. First, sender and receiver may not connect to the same chat server. HTTP-based servers are usually stateless. If you use round robin for load balancing, the server that receives the message might not have a long polling connection with the client who receives the message. A server has no good way to tell if a client is disconnected. It is efficient. If a user does not chat much, long polling still makes periodic connections after timeouts. So this is how long polling works. And now the last part is the WebSocket. WebSocket is the most common solution for sending asynchronous updates from server to client. And as you can see in the figure, this is how WebSocket works. WebSocket connection is initiated by the client. It is a bidirectional and persistent. It starts its life as a HTTP connection and could be upgraded via some well-defined handshake to a WebSocket connection. Through this persistent connection, a server could send updates to a client. WebSocket connections generally work even if a firewall is in place. This is because they use port 80 or 443, which are also used by HTTP or HTTP connections. By using WebSocket for both sending and receiving, it simplifies the design and makes implementation on both client and server more straightforward. Since WebSocket connections are persistent, efficient connection management is critical on the server side. This is how the protocols work, and for our chat system is a bidirectional communication we need, so we will be using WebSocket communication in this chat system. Now let's look into our next detail, which is related to end-to-end flow of a chat system, which is basically like one-on-one versus group chat. So first we will discuss about one-on-one chat flow, how it works. User A that sends a chat message to chat server 1. Chat server 1 obtains a message ID from the ID generator. Then chat server 1 sends a message to the messaging queue. The message is stored in a key value store, and if user B is online, then the message is forwarded to chat server 2 where user B is connected. If user B is offline, then push notification is sent from push notification servers. Chat server 2 forwards the message to user B. There is a persistence WebSocket connections between user 3 and chat server 2. So this is how our one-on-one chat flow will work. Many users have multiple devices. We will explain how to sync messages across multiple devices. Now, in message synchronization between multiple devices, as you can see the flow, user A has 2 devices, phone and a laptop. When user A logs into the chat app with her phone, it establishes a WebSocket connection with chat server 1. Similarly, there is a connection between the laptop and chat server 1. Each device maintains a variable called current message ID, which keeps track of the latest message on the device. Messages that satisfy the following two conditions are considered a new message. The first one is the recipient ID is equal to the current login user ID. And second is message ID in the key value store is larger than the current message ID. With distinct current message ID on each device, message synchronization is easy as each device can get new messages from the key value store. Now let's look into small group chat flow. Again, like small group chat flow works differently than a larger group. For larger group, we have, let's assume that there are like more than 500 users in a group. As an example, when you're working in a company and you're planning to send out like a product launch announcement to the whole company, you might send out an email or message. You might send out a message to the larger group in a Slack. So for larger group, the flow will be different, which we will discuss after the small group chat. So for small group chat flow, this is how it looks like. Basically, what happens when user A sends a message to a group chat? Assume there are three members in the group, user A, user B, and user C. First, the message from user A is copied to each group member's message sync queue, one for user B and one for user C. You can think of the message sync queue as basically an inbox for a recipient. This design choice is good for small group chat because it simplifies message sync flow as each client only needs to check its own inbox to get the new messages. And when the group number is small, storing a copy in each recipient's inbox is not too expensive. But now, let's think about the same scenario for a larger group. Like let's say there are 500 users in a group. Storing a message copy for 500 users is really not practical. It's not good. It might become expensive for us. So in that case, how would we do it? So this is the flow for a large group chat flow, as you can see. Basically, like when users are sending out messages, there might be a chance that in large group chat, there might be multiple users sending out message at the same time. So instead of having separate message queue for each and every users, we will just have a common message queue where we will receive all the messages from multiple users. Each recipient has an inbox which contains messages from different senders. And that's how like other users will keep getting messages from the same message queue. Now, let's discuss about users' online or offline status. How does it work? So first, let's discuss about online status. When user logs in, we will send a request to PN server, basically present servers, and then present server will save data into the key value store, where we will save the status as user is online, and the last timestamp for online is X. And this is how we will maintain the online status. For offline status, when user logs out, we will send a request through present server, and present server will send a request in key value store where we will save the status as offline because usage got disconnected. Now, this flow sounds very simple and straightforward where you just mark it online and offline, but this is really not practical. Why? Because when user is online, there might be a chance that they got some internet issues or network issues. In that case, the request will not go through present server. And in that case, even the user is not online, other friends in that group will see them as online, which is basically like a misguiding other users or other friends. So how do we make sure that user is really online or not? Next, I will show you how. So here, as you can see, instead of sending request manually through present server that, hey, this user is online or offline, what we will do here is client, basically like user side client, we will send requests every 5 seconds to present server. If present server reaches heartbeat every 5 seconds, it means the status is online, the user is still there. But after waiting for 30 seconds, if PN server is still not getting any heartbeat, it means the user is offline. Maybe because of internet issue, or user really got disconnected, or user had logged off. There are multiple reasons, and this is how we will know that user is really online or offline. Now, next we will move with online status when out, which is basically like when there is a small group chat or large group chat, how things will work in that case. How do we maintain that all the users who are part of this group chat, they are online or offline? So as you can see here, basically there is a user A, and when they log in or when they are available, we will send a request to multiple channels, and all the groups or members who are subscribed to this particular group, they will be getting the message through this channel that this is the online status or offline status, and this is how everything will be updated. This works well for small group chat, but when it is a larger group, like maybe 500 users or 1,000 users or maybe 100,000 users as part of the group chat, in that case, this is not a great idea. Why? Because if there are like 500 users or maybe 1,000 users, we will have to generate almost 500 or 1,000 events, which is not a good idea. So how do we manage in that case? And how do we inform other users who are part of this group chat? Basically, when there is a larger group, what we will do in this case is, instead of signing event for each members part of that group, we will basically, when other group members comes in online, we will update the status at that time only, instead of sending it to message event. So that we save all the unnecessary message event. That's one way to do it. A second way to do it is, let's say all the members are already online, but when they send a manual refresh update, only at that time we will refresh the status of all the group members who are part of that group. That way, like, we don't waste unnecessary events. It is just done when it is really needed to be done. So these are the two main requirements which we deep dive into. One is like online offline status updates, and another is like one-on-one versus group chat. Now let's discuss about message history and read receipts. First, we will discuss about message history. So user A, let's say user A opens a chat window with user B or group. The client app sends a fast message history request to the chat server via load balancer. Chat server checks the cache for the most recent messages of that conversation ID. If found, then return those messages immediately. This gives us low latency. If not found, proceed to the database lookup. Chat server queries the database for messages in that conversation. Usually paginated last 50 or 100 messages. Data is stored using conversation ID plus timestamp as partition or sort case for efficient lookups. Retrieve messages are returned to chat server and which is in the end visible to the user. And this is how our message history will work. Now let's look into the next flow, which is read receipts. How does read receipt work? So user A, which is assigned here, sends a message. The request goes to the chat server via WebSocket. Persists the message in the database or through message in the database, and at that point, in the database, we will mark the status as sent. Then sends an acknowledgement back to user A confirming it is already sent and it is already saved. Now, once it is sent, we also need to consider that if message is really delivered or not. So message queue publishes the message to chat server 2, which has an active connection with user B. Chat server 2 pushes the message to user B's client. Once user B's client acknowledges the receipt, chat server 2 updates the message status to delivered in the database or cache. A delivery update event is published back through the queue or notification service to chat server 1, which updates the user A's UI, that status. Basically, it will update the status as delivered. Now, in the end, our goal is, how do we know if the message is read? So when user B, who is the receiver, opens the chat or reads the message, the client sends a read receipt event to chat server 2. Chat server 2 will update the message and to read in the database or cache. It will publish the event to the message queue, and then message queue routes this read event to chat server 1, which updates user A's client UI, and it will inform the user A that message is already read by user B. This is how our read receipt flow will work. Now let's look into our non-functional requirements. Low latency. In chat system, low latency is very critical. Users expect messages to appear instantly. Our design focuses on reducing round-trip time at every layer. Main key points are persistent WebSocket connection, which is really needed. Each user keeps an open WebSocket connection with the nearest chat server. It offers repetitive HTTP handshakes and current latency 2 milliseconds. Then, geo-distributed chat servers. Deploy chat servers across regions. Route users to their nearest region using the load balancer. A third way to reduce low latency is basically in-memory caching. Store recent messages, user status, and read receipts in Redis or Memcache to avoid DB lookups for hard data. And the last one is async message processing. which is basically the message queue ensures that the sender isn't blocked while the message is persisted and found out. So for example, when user A sends a message, it goes through the closest chat server over a persistent WebSocket, gets queued asynchronously, and is delivered to user B almost instantly, typically under 100 milliseconds. Now let's look into our next non-functional requirement, which is scalability. A chat app can start with thousands of users and scales to millions. We need horizontal scalability at every tier. Chat server. Make sure it is stateless and can be scaled horizontally behind the load balancer. New servers can be added to handle more concurrent WebSocket connections. Then message queue. Partition by chat room or topic. We can use any type of message queue like Kafka, RabbitMQ, or AWS SQS. It supports parallel processing and balanced consumer load. Then database. For database, we can use sharding by conversation ID or user ID, which ensures data is evenly distributed. Cache tier. We can use Redis cluster for distributed caching for fast lookups. And then last one, which is present servers. Each server handles a subset of users' heartbeat traffic, scaling independently. For example, because each chat server is stateless, we can just spin up new instances when traffic spikes. All user connections are balanced automatically, and messages are still routed correctly through the server shared queue. Now, next let's look into reliability. Reliability ensures that no messages is lost even if components crashes or users disconnect temporarily. So first, durable message flow. Message queue ensures at least once delivery. Messages are persisted before being consumed. In terms of acknowledgements, sender receives a message sent acknowledgement only after it's stored in the key value stored. Then, idempotent writes in the DB. Duplicate deliveries won't cause multiple inserts. Repair mechanisms for transient failures, which is also already part of message queues. And then message status tracking. We should always track message status, which confirms delivery integrity. Now, in terms of offline reliability, for offline users, message stays in the DB until retrieved later. And for notification service, triggers push notification for offline users. For example, even if user B is offline, the message remains safely stored in the database and will be delivered the next time they reconnect. Reliability means no message ever gets dropped. Now, our last non-functional requirement, which is fault tolerance. Fault tolerance ensures that even if a server or data center fails, chat continues smoothly. In terms of redundant instances, multiple chat servers, message queue brokers, and DB replicas across availability zones. Clear election and replication in the message queue and DB layers. Then, automatic failover using orchestration tools like Kubernetes, load balancer, hot checks. We can use all those things. And if the DB is slow, serves from cache. For graceful degradation, we can also look into if present server fails, message to work. And for heartbeat monitoring, continuous checks component health, removes unhealthy nodes from rotation. So for example, if one chat server or broker crashes, the load balancer instantly reroutes traffic to a healthy node. And Kafka ensures message persistence across replicas. Users won't even notice the failure. So we cover almost all non-functional requirements. So let's wrap things up. In this video, we designed a complete chat system from the high-level architecture to the deeper details of how each part works. On the functional side, we looked at 4 key features that make up a modern chat experience. One-to-one and group chat, where we walk through how messages travel from one user through the chat servers and message queue to reach one or many recipients. Online and offline status, handled by present servers using periodic heartbeats and a pub/sub model for fan-out updates. Message history, so users can retrieve past conversation through cache-first lookups backed by your database. Read receipts, showing sent, delivered, and read status, using event updates stored and propagated through our system. Then, we looked at the non-functional requirements that make this design production ready. Low latency, achieved through WebSockets, in-memory caching, and asynchronous message processing. Scalability, by keeping our chat servers stateless and scaling horizontally with partition queues and shared database. Reliability, ensuring messages are never lost through durable queues, acknowledgements, and return mechanisms. Fault tolerance, by replicating components deploying across availability zones and enabling automatic failover. Altogether, this architecture gives us a chat system that's fast, reliable, and scalable, capable of supporting millions of concurrent users while maintaining real-time communication. And remember, in real system, design is always about trade-offs. You might tune consistency versus latency or prioritize cost versus redundancy depending on scale and business needs. Thank you everyone. If you like the video, please click on like button.